y less than or equal to 0 consists of a perfect conductor. A perfect conductor. While region y greater than or equal to 0 is a dielectric medium epsilon 1 r is equal to 2. If there is a surface charge of 2 nanocoulomb per meter square on the conductor, determine E and D, that is electric field and flux density at A 3, point 3, minus 2, 2. B is point minus 4, 1, 5. So this is a given question. So here also we have to apply boundary conditions to solve this problem. The solution is, draw a rough figure. Here this is y is equal to 0 plane. So region y less than 0. So y less than 0 means this. Y greater than or equal to 0 means this. Region y less than or equal to 0 is a perfect conductor. So this is a perfect conductor. Region y greater than or equal to 0 is a dielectric medium. So this is dielectric. This is dielectric with epsilon 1 r is equal to 2. So there is a surface charge density rho s equal to 2 nanocoulomb per meter square on the conductor. Determine E and D at 2 given points. So the first one is A. What is the given point? Point is 3, minus 2, 2. So here they are discussing about y is equal to 0 plane. Y is equal to 0 plane. So you concentrate on y coordinate only. So here for this point y is minus 2. So y is minus 2. So minus 2 means the point is here. The point is in y less than or equal to 0 region. 3 minus 2, 2. The point is in this region, the A point P. That is the point is in perfect conductor region. So since point P lies in the region y less than or equal to 0. So perfect conductor means what is electric field? Electric field is equal to 0. Implies D is also equal to 0. Inside a perfect conductor, electric field is 0. Implies flux density is also 0. So E is equal to 0, D is equal to 0 for point P, 3, minus 2, 2. Since it lies in region y less than or equal to 0. So that is very clear. Suppose next B. The B question is, point is minus 4, 1, 5. Suppose here y is equal to 1. Y is 1. So this is the point lies here, minus 4, 1, 5. So the point is in dielectric medium. Then what is the electric field and electric flux density we have to calculate. Since perfect conductor E1n is equal to 0, E1t is equal to 0. Similarly D1n is equal to 0, D1t is equal to 0 in region 1. Therefore we have to calculate E2 in this region, E2. So E2 is equal to E2t plus E2n. E2t plus E2n. E2t is 0 because first boundary condition is E1t is equal to E2t. So that is equal to 0. So we have to calculate E2n. This is first boundary condition I am applying. What is the second boundary condition? d1n minus d2n is equal to rho s. Since d1n is equal to 0, d2n is epsilon to e2n is equal to rho s. e2n is equal to rho s by epsilon 2. Rho s by epsilon 2. Rho s is 2 nanocoulomb per meter square by epsilon 2 is epsilon naught into epsilon r2. Therefore, E2 is equal to E2n, that is 2 into 10 power minus 9 nanocoulomb, that is because of nanocoulomb, this 10 power minus 9 is for nanocoulomb, into epsilon naught is 10 power minus 9 by 36 pi. So this 36 pi numerator by 2 into epsilon 1r is 2. So 2 into 10 power minus 9. What is the direction? AY direction. Because it is given y is equal to 0 plane. So normal is along AY. So if you simplify this, E2 is equal to 36 pi AY. Here you have to consider magnitude. Because here this formula is y less than 0 is medium 1, y less than greater than or equal to medium 2. So here we don't know exactly what is medium 1 and medium 2. So that's why in general you consider, if they didn't mention what is medium 1 and medium 2, you consider magnitude value. Then you will get exact answer. Suppose if they mention medium 1 and medium 2, then there is no problem. That's why here I am considering, generally this is not, I am not considering negative sign here. Magnitude value only I am considering. So at this particular point E2 is equal to this much. So once E2 is known, then you can calculate D. Then you can calculate easily D value. So this type of problems are very important. Now we will solve some problems in electrostatics. The first problem is plane Z is equal to 10 meters carries charge 20 nanocoulomb per meter square. The electric field intensity at origin is option A minus 10 AZ cap volt per meter, option B minus 18 pi AZ cap volt per meter, option C minus 72 pi AZ cap volt per meter, option D minus 360 pi AZ cap volt per meter. The solution to this problem is, here it is given Z is equal to 10 plane. So Z is equal to 10 plane means a plane like this at this particular point carries charge 20 nanocoulomb per meter square. So here it is given rho s, because this is a sheet, surface charge is given 20 nanocoulomb per meter square. Then what is the electric field intensity at the origin? So origin means this one. So this is the sheet. having rho s 20 nanocoulomb per meter square. So origin means here, that is the point of interest here is below the plane, below z is equal to 0 plane. So the field intensity, the normal is in this direction. So we know that the electric field intensity due to infinite sheet is rho s by 2 epsilon naught an cap, where an is normal vector to the plane. Here an bar is minus az, since the point of interest is below z is equal to 10 plane. Therefore electric field intensity is rho s is given 20 nanocoulomb. So 20 into 10 power minus 9 by 2 into 10 power minus 9 by 36 pi minus az cap. So this 10 power minus 9, 10 power minus 9 cancels. This is equal to this is 2 tens, so 36 pi into 10, so minus 360 pi az cap. So this is the electric field intensity. Here you observe the options, all options are in terms of pi only. So option D is correct. Problem 2 is, next problem number 2. Point charges (30 nanocoulomb, minus 20 nanocoulomb and 10 nanocoulomb) are located at minus 1, 0, 2, 0, 0, 0 and 1, 5, minus 1 respectively. The total flux leaving a cube of side 6 meter centered at origin is option A minus 20 nanocoulomb, option B 10 nanocoulomb, option C 20 nanocoulomb, option D 30 nanocoulomb. So this is the given problem. The solution to this problem is, here they are asking the total flux leaving a cube of side 6 meters centered at the origin. So this is the cube. A cube is like this. Cube is like this. This is centered at origin. So suppose this is origin. This is X. This is Y. Suppose like this, centered at origin. X, Y, Z. That is, each side is 3 meters. Each side is 3 meters. This is 3 meters. This is 3 meters. Each side is 3 meters around the origin. Here they are asking total flux leaving. Total flux leaving. So we have to use Gauss law. So by using Gauss law, total flux leaving a volume is nothing but total charge enclosed. Total charge enclosed within the volume. So here 3 point charges are given. Here the point charges are given at a particular point. That is, if you observe the first point, minus 1, 0, 2. So X is minus 1, Y is 0, Z is 2. So all values are within 3. All x is lies between x is within 3. That is because x is 3 to 3. Because side is 6 meters means negative side minus 3, positive side 3. So x is minus 1 means it is below minus 1, minus 3. So here minus 1. Similarly y is 0, that is 2. So it lies in the cube. So this point lies in the cube. Lies in the cube. So this is 30 nanocoulomb. Similarly, if you come to second point, 0, 0, 0 means origin. Origin minus 20 nanocoulomb. So this is also lies in the cube. If you come to next point, 1, 5, 1, 1, 5, minus 1, which is 10 nanocoulomb. If you see this point, here y value is 5. Y value is 5. Y value is 5. So y value 5 means this is greater than 3. So this point is out of the cube. Out of the cube. So only these 2 points, first and second points are lies within the cube. So the total charge within the cube is Q enclosed is equal to 30 minus 20, that is 10 nanocoulomb. Therefore, total flux leaving the cube is 10 nanocoulomb. Total flux leaving is 10 nanocoulomb. That is option B is correct. Option B is correct. Option B. Option B is correct. Next problem is problem number 3. The work done by the force F is equal to 4ax minus 3ay plus 2az Newton in giving a 1 nanocoulomb charge a displacement of 10ax plus 2ay minus 7az meters is option A 103 nanojoules, option B 60 nanojoules, option C 64 nanojoules, option D 20 nanojoules. Solution to this problem is, here a 1 nanocoulomb charge is there. So the work done by the force F in giving a 1 nanocoulomb charge a displacement of this. So I am applying some force to displace this charge to a distance, suppose dl. Then what is the work done for this process? We know that the work done is equal to minus F into dl. Minus F into dl. That is minus F dot dl. F dot dl means 40 minus 6 minus 14. This is nothing but minus work done is F dot dl. Work done is F dot dl. So this is plus 20. Work done is 20. Since here we are moving a 1 nanocoulomb charge, so the work done is also given by 20 nanojoules. So option D is correct. Next problem is problem number 4. A medium is divided into two regions, 1 and 2. About x is equal to 0 plane as shown in figure below. An EM wave with E field E1 is equal to 4ax cap plus 3ay cap plus 5az cap is incident normally on the interface. From region 1. The electric field in region 2 at the interface is the given figure is like this. This is region 1, this is region 2. Sigma 1 is equal to 0, mu 1 is equal to mu 0, epsilon r1 is equal to 3. Sigma 2 is equal to 0, mu 2 is equal to mu 0, epsilon r2 is equal to 4. So E1 is like this. They are asking what is E2 at interface. This is E2 at interface x is equal to 0. At interface they are asking what is the electric field. So the options are E2 is equal to E1. Option B is 4ax plus 0.75 ay minus 1.25 az. Option C is 3ax plus 3ay plus 5az. Option D is minus 3ax plus 3ay plus 5az. So the solution to this problem is, here electric field is given E1 4ax plus 3ay plus 5az. We know that we can write this as some E1t plus E1n. Since it is given x is equal to 0 plane, the normal component is ax. Because x is equal to 0 plane means it is a yz plane. So what is the normal component to yz? Ax. So ax is the normal component. So E1t is equal to 3ay plus 5az. E1n is equal to 4ax. If you apply the first boundary condition, E2t is equal to E1t. First boundary condition, that is equal to E1t 3ay plus 5az. What is the second boundary condition? D1n minus D2n is equal to rho s. Here rho s is equal to 0. Therefore D1n is equal to D2n. That is epsilon 2 E2n is equal to epsilon 1 E1n. So E2n I want epsilon 1 by epsilon 2 E1n. So what is epsilon 1? 3 by epsilon 2. 3 by 4 into E1n. E1n is 4ax cap. So 4 cancels, that is equal to 3ax. Therefore total E2 is equal to E2t plus E2n. E2t is 3ay plus 5az, 3ax. So 3ax plus 3ay plus 5az. So if you compare, the answer is option C. Option C is 3ax plus 3ay plus 5az. So here we are applying boundary conditions to solve this problem. So half of the problem is in the given question itself, of the solution. That is, just we have to identify what is the tangential component and what is the normal component in the given electric field. So since tangential component is continuous at the boundary, so tangential part of electric field 2 is equal to tangential part of electric field 1. So just we have to find normal component. So this type of problems are important.